I think we'll go ahead and get started. So just to remind you of where we left off in the previous lecture. So we started discussing a new topic, which is the topic of state estimation. So basically, how can a robot use its potentially imperfect sensors to get a decent estimate of its state, which it can then use to do things like feedback control. And the main technique we discussed in the previous lecture is this thing called the non-deterministic filter, which is sort of like a conceptual algorithm. It's not something that one implements in practice, but it's going to be the conceptual basis for techniques that do get used in practice, which we're going to start discussing today. And I guess just to remind you of the structure of the algorithm, which again we're going to revisit today, is you start off with some initial estimate for where the state of the robot could be. So this estimate takes the form of a set that we're going to call, or that we did call x0 hat. We then propagate this set forward through the dynamics of the system, which initially at least we were assuming were deterministic. We get some other set, which we called f of x0 hat. And I guess just to remind you, we're using discrete time dynamics here. So xt plus 1 is f of xt. And then potentially you can bake in the control input as well. And then we also had a sensor model, which was given by this function h. So at any given state, xt, we know what the sensor measurement the robot is going to get. So the robot gets a sensor measurement, which helps it narrow down which set of states it could be in. So we introduced this concept of the pre-image. So the pre-image is the set of all states that are consistent with the robot receiving the sensor measurement that it received, which we're calling ZT. And then we take the intersection of these sets. So we say that x1 hat, which is our new estimate for where the state can be, is simply the intersection sorry, let's say this is Z1, the first time step. So it's the intersection of these two sets. So the initial set propagated through the dynamics, and then the pre-image of the sensor measurement that the robot receives at time step 1. And in general, the steps for the non-deterministic filter are the following. So at every time step, so we do this kind of recursively. So we first take our previous estimate of where the state can be. We propagate that through the dynamics. So compute f of x hat t minus 1. And in the second step, you compute the pre-image of the sensor measurement that you received at the current time step. So pre-image of ZT. And then finally, you take the intersection of these two sets. So x t hat is f of x hat t minus 1 intersected with the pre-image. So we're using our knowledge of both the dynamics and the sensor model. So this step is typically called the dynamics update. So we're updating our estimate of where the robot state could be based on our knowledge of the dynamics. And then these two steps, well, yeah, I guess it kind of depends on the context, but either this step or usually these two steps combined is called the measurement update. Where we incorporate the new measurement, the new sensor measurement that the robot receives, combine that with our knowledge of the dynamics to get an updated estimate of where the state can be.
On the next way, you write is equals to fx. No, what is equals to? Is it fx hat?
Sorry, yes, yeah. Yeah, it's from outer space. X1 hat. Yeah, X1 hat. So our new estimate of where the state can be is the previous estimate propagated through the dynamics intersected with the pre-image of the new sensor measurement.
And then move this pointing.
Yeah, sorry, this is not the best picture. This is pointing at the intersection of the two sets. Yeah. Good. All right. Okay. Right. So I guess as we discussed in the previous lecture, actually calculating these sets, especially in like high dimensions. So even like high here means even like for a drone, 12-dimensional state space. These things can be like pretty hard to compute. Calculating intersections, representing these sets in a kind of computationally efficient way. All of that is challenging. So we don't typically implement this. The other kind of major conceptual problem with this non-deterministic filter is that at every time step, the thing that we're maintaining is a set. So a set of possibilities for where the state can be. And if we're trying to do something like feedback control, we really need a bit more of a refined estimate of where the state can be. So we need to somehow maybe pick out a representative element from that set, or do something else to apply a feedback controller. So that's what we're going to try to fix. So the kind of second problem, the problem of not just maintaining a set of possibilities, but maintaining a more kind of refined estimate of the state. So the topic for today is going to be to discuss probabilistic methods for state estimation. And yeah, these methods are also going to then allow us to do things like mapping the robot's environment and localizing and so on. But today we're just going to focus on the problem of estimating the state. Question?
Yeah, so in our previous formulation, are we assuming our environment is discrete?
Okay, so we're not necessarily assuming that the environment is discrete in the sense that we have like a finite or discrete number of states. So the state space can still be continuous, and the non-deterministic filter is still well-defined in that setting. The discreteness here is in terms of time. So we're assuming that yeah, the world is evolving kind of time step to time step, and it's not a continuous time model. And we kind of keep that same kind of structure. Today, the algorithms I'll describe will work, at least conceptually, if not necessarily computationally efficiently, for continuous state and control input spaces and sensor measurement spaces, but still discrete time. All right. So yeah, as I mentioned, so probabilistic methods for doing state estimation, and the main idea and the kind of key difference between what we're going to discuss today and what we discussed with the non-deterministic filter in the previous lecture is that we're going to maintain what's known as a belief in this kind of literature on probabilistic state estimation. So maintain a belief, which is really just a probability distribution over the state. So instead of just having a set of possibilities, this is a slightly more kind of refined quantification of our uncertainty about where the state of the robot can be. And so I guess what I'm going to start off with is just a quick recap. I mean, hopefully it is a recap of just some basic probability concepts. So I realize that, yeah, I guess people have many different backgrounds, and especially I found like students with an MAE background often haven't seen probability in a long time, so I'm going to just do a quick recap of some basic probability concepts. And I'll also point you to a chapter in the textbook here. So a good reference for all of this material on probabilistic state estimation and so on is the book on probabilistic robotics. And I linked, I think, to this book in the slides in the very first lecture. And I think it's referenced in the syllabus as well, so you should be able to find it. And chapter 2.2 in this book has a pretty nice recap of these probability basics. So the first thing is just defining some notation. So the main notation looks something like this. So we have a random variable, which is typically denoted by capital X, which can take on values which are denoted by little x. So you can think of this as coin flips, for instance. So which side the coin comes out on when you flip it is the random variable. The specific, like head or tails, is the value that the random variable takes. So this is the probability that the random variable x takes on value little x. So for instance, the probability that x is heads could equal the probability that x is tails, which is 0.5 for an unbiased coin. And usually we won't kind of write everything out fully like this. We're just going to abbreviate. So we'll write just p of little x. And yeah, from context, like it should be clear that what we really mean is that this is the probability that some random variable like takes on value little x. So we'll typically use just this abbreviated notation. So we'll write like probability of heads, or like probability of tails, like without explicitly writing the random variable. Okay, so yeah, I guess that's the most kind of basic piece of notation. And one basic fact about probabilities, maybe the most kind of basic fact, is that probabilities sum or integrate to 1. And whether we look at summations or integrals depends on whether the random variable takes on a discrete set of values or potentially a continuous set of values. So in the discrete setting, this corresponds to a summation over all the possibilities, little x of p of x equals 1. And in the continuous setting, so if we're looking at things like distances, like range measurements that a robot's range sensor gives it, then we look at integrals over x, p of x, dx equals 1. Okay. The other, I guess, important concept is that of a joint distribution. So if we have multiple random variables, let's say 2 random variables, then we denote the joint distribution by p of x comma y. And again, this is really shorthand for saying that this is the probability that the random variable capital X takes on value little x, and the random variable capital Y, and random variable capital Y takes on value little y. So if you have two coins that you're tossing, the outcome of the first one could be denoted by x, the second one by y, for instance. All right. And then if you have independent random variables, so two independent random variables, then the joint distribution over x and y is just the product p of x multiplied by p of y. All right, the next important concept, which we're going to use quite a bit in today's lecture, is that of a conditional distribution. So we're going to denote this by p of x with a bar, so p of x given y. And again, this is really shorthand for saying that this is the probability that random variable capital X takes on value little x, conditioned on the random variable capital Y taking on value little y. And by definition, so we're just going to define this notion of conditional distribution from these previous notions of joint distribution. So we're going to define p of x given y as p of x comma y, which is the joint distribution divided by p of y. And this assumes that p of y is not equal to 0, otherwise we're dividing by 0, and this is not defined. So as long as p of y is strictly larger than 0, we can define the conditional probability distribution as such. And just as a, I guess, sanity check, so we can see what happens if x and y are independent. So this over here. So in that case, the conditional distribution p of x given y, you would expect intuitively is just equal to p of x, right? So y is not giving you any information about x, so y doesn't inform your probability on x. So by definition, this is p of x comma y, p of y, and then if x and y are independent, then just kind of by definition here of independence, the joint distribution equals the product divided by p of y. And again, we're assuming p of y is not equal to 0, and so this is then p of x, which checks out just kind of intuitively. All right. I guess any questions after this? Okay. All right. Just a couple more facts about probabilities.
I have a question.
Yeah. Go ahead.
Just like, what does that mean conceptually? That x, does it mean it doesn't depend on y? Like, is that what our check is saying?
Yeah, so it's independent of y, right?
Oh, I see. Okay.
Yeah, yeah. So if you have like two coins that you're flipping, just, I guess it's hard to avoid the word independently, but yeah, independently in the kind of colloquial sense, you just flip two coins one after the other, then that's an example. of that, of independence. And so the probability that your second coin comes up heads, given that the first one came up tails, like the fact that the first one came up tails doesn't matter. And so the probability that the second one comes up heads is just the probability that the second one comes up heads, which is 0.5 for an unbiased coin. All right, good. Other questions? Okay, so yeah, another I guess important fact is what's known as the theorem of total probability. Which actually follows, so this might be a useful exercise to prove this from the definitions we gave above. So this states that P of x is equal to the summation over y of the joint distribution, which is the same as, so the joint distribution, if you look at our definition of the conditional distribution up there, is P of x given y multiplied by P of y. So this is in the discrete setting. So when you have a discrete set of possibilities for what x and y can take on, in the continuous setting, we simply replace the summation with the integral. Yeah, and as I mentioned, this fact, this theorem of total probability follows from the facts that we stated before, and might be a useful exercise just to go through that and prove that. And this quantity, so the P of x, is then known as the marginal distribution. So the marginal distribution on x. All right, and then the final result, which is, I guess, the most important one in our context, is Bayes' rule. Oh, it's still not erasing cleanly, even with the new chalk. Maybe I'll try to figure this out over the break. Yeah, okay. All right, so yeah, the most important result is Bayes' rule. So this, let me state it in the, let me just state it and then I'll prove it using the results we discussed before. So P of x given y is equal to P of y given x multiplied by P of x divided by P of y. So this is Bayes' rule. We can write it in a slightly different form by expanding out the denominator. So P of y given x divided by P of x. We can expand out the probability of y using this law of total probability. So we can write the denominator as a summation over x of P of y given x multiplied by P of x. Okay, so yeah, I guess this equality just follows from the law of total probability, which we wrote over here. It's kind of inverted. I wrote it in terms of summation over y. Here we're summing over x, but it's the same thing. This one, this equality, this is like Bayes' rule, so we can prove this using some of the previously introduced concepts. So the proof is if we look at P of x comma y, so that's the joint distribution, I can write this in two different ways. So I can write this as P of x given y multiplied by P of y. And this follows from the definition of the conditional distribution that we wrote over there. So just multiplying both sides by P of y up there. Or we can also write this joint distribution P of x comma y kind of in the other way. So P of y given x multiplied by P of x. Again, using the definition of the conditional probability distribution. And so now we can just rearrange the terms here. So dividing both sides by P of y, assuming it's not 0. So P of x given y is P of y given x, P of x divided by P of y. All right. Okay, yeah, I guess any questions on this? So the main reason Bayes' rule is important, so one way to kind of interpret it is that it's allowing you to invert conditional probabilities. Right, so here what we're trying to calculate is P of x given y. What we have on the right-hand side over here is P of y given x. It's kind of the inverse conditional. And this kind of inversion is often exactly what we want to do for state estimation, for instance. So I'm kind of previewing what we're going to do, but yeah, just to give you a high-level idea, we're going to assume that we have some probabilistic sensor model. So some probability distribution that tells us probabilities over the sensor measurements, which in this case, let's say, are represented by y, given that the robot is in state x. What we actually care about is not that. We care about the inverse, right? So we care about what's the probability that the state is something given that the robot received some sensor measurement y. And that's exactly what, that kind of inversion is exactly what Bayes' rule allows you to do. Okay, we'll see that in much more detail as we go along. All right, yeah, and I guess as I mentioned, if you're kind of rusty on some of these probability basics, the chapter 2.2 from the probabilistic robotics book gives you a bit more background. Okay, so what I'm going to do is just look at a specific example. And then we'll kind of generalize things to a broader setting. So the example is adapted from section or chapter 2.4.2 in the probabilistic robotics book. I made some small modifications to it just so I can kind of fit it in one lecture, but it's basically the same example if you want to take a look. So in this example, we have a robot. This is my stick figure drawing of a robot that's looking at, let's say, like a building. And there's a door in the building. So yeah, this is the world that the robot is operating in. And the state of the world, so the entire state of the world has to do with whether the door is open or not. So in this case, so for this example, I guess there's a question about whether we have continuous or discrete variables. Here, the state is discrete. So there's actually just two possibilities, either the door is open or closed. As I mentioned, we'll go through this example and then generalize to a broader setting. Let me just write it out. So the state here which we're going to denote by capital XT. So you can think of this as a random variable, corresponds to door open or not. All right, and the robot is equipped with some imperfect sensor. Which gives it some information about the state of the world, so about whether the door is open or not, but it's not 100% accurate. And more specifically, so I'm going to write down a specific sensor model. So the probability, so this imperfect sensor gives you some sensor measurements, which we're going to call ZT. So the sensor measurement at time t. And this is going to be a random variable. And I'm going to define the probabilities for this random variable. So the probability that the robot, so this is an underscore, so sense underscore open. So the sensor measurement reports that the door is open, given that the door is actually open, is some, let me just erase this. Some value, so we're going to say it's 0.6. And then the probability that the sensor reports that the door is closed, given that in fact the door is open, is just 1 minus 0.6, so the probabilities have to sum to 1, so it's 0.4. And then the other way, so the probability that the robot senses that the door is open, given that the door is in fact closed, is 0.2. And the probability, finally, that the door is sensed to be closed, given that the door is in fact closed. So this is just 1 minus 0.2, which is 0.8. All right, so this is our probabilistic model of the sensor. We're going to assume that this is given to us. So given to us, like the robot designer, or somehow we've acquired it. And I guess one thing to note here is that we're saying that the sensor is a bit more accurate when the door is closed. Right? So when the door is closed, the probability that the robot senses that the door is closed is relatively high, so it's 0.8. And the probability that makes a mistake is 0.2. And when the door is open, the robot is slightly less, so the sensor is slightly less accurate. So the probability that the robot senses that the door is open, given that the door is in fact open, is 0.6 rather than 0.8. So I guess one question here to consider is how would you get a model like this? So we're going to take this as an input, but in practice we're going to have to actually acquire some kind of probabilistic model like this. So what is this, I mean, conceptually even, like how would you go about getting a model like this in practice? Go ahead.
You would just do a very long, tedious experiment
Yeah.
where you like either leave the door open and then like sense it and
Yeah.
like, leave the door closed and sense it.
Yep.
You might have to be careful of like just doing all your open trials and then all your closed trials because it might be so efficient.
Yeah, that's exactly right. So this is basically acquired with tedious experiments, right? So you just keep your sensor in front of an open or closed door, do this experiment multiple times, and then look at the empirical probabilities, and then you can take that as your probabilistic model. So yeah, we're going to assume that that experiment has been done. We've characterized the errors that the sensor makes. And then given this probabilistic model of the sensor, we're going to try to do state estimation. So that's the plan. Okay, so So yeah, let's say, I guess one more piece of information that we're given is what we're going to call a prior belief about whether or not the door is open. So this is the probability that the robot assigns to the door being open or closed before it starts kind of operating in the world. So before it receives any sensor measurements, before it does anything, the robot just has some prior belief about whether or not the door is open. Here we're just going to make kind of a simple choice. So we're going to say that the probability, the prior probability that the door is open equals the prior probability that the door is closed equals 0.5. And so the random variable here, so this is the state of the door at time step 1, is open or closed. We're just going to say it's 0.5. So it's equal probability that the door is open or closed. In practice, I guess you could kind of do another experiment here. So you go around all of campus, maybe even more. Just count the number of doors that you see open or not. And that can inform this prior belief about whether any new door is going to be open or closed. We're just going to say it's 0.5 for now. Okay, so I guess here's where it starts to get interesting. So at time step t equal to 1, let's say, so the first time step, the robot receives some sensor measurement. And specifically, just for concreteness, let's say the robot senses that the door is open. And now, given this sensor measurement, and given what it knows about the error characteristics of the sensor, and its prior belief over whether or not the door is going to be open or not, it needs to update its belief about whether or not the door is open. So we're going to denote this updated belief by BEL, short for belief. This is the notation that the book uses as well. So the probability, so this is the probability that the door is open at the first time step, or I guess the belief that the door is open, the updated probability that the door is open, updated given this new sensor measurement at time step 1. So we can, so really what this is like the probability that the door is open, given that we sense that the door is open, right? So that's what we're assuming the robot senses. So this is where Bayes' rule comes in. So we have this conditional probability that the door is open given the sensor measurement. We can apply Bayes' rule here. So P of x given z is P of z given x multiplied by P of x divided by P of z. So we can plug in some, I guess any questions on that? All right, so we can plug in some numbers to make this more concrete. So let's look at the numerator first. So the numerator is P of z is sensed to be open given that the door is in fact open. So that comes from our probabilistic model of the sensor, right? So the probability that we sense the door to be open, given that the door is in fact open, is equal to 0.6 by assumption, multiplied by the prior probability that the door is open, and that, again, by assumption is equal to 0.5. So that's the numerator. The denominator we can expand using the law of total probability. So the probability that we sense the door to be open, we can expand out as the probability that we sense the door to be open, given that the door is open, multiplied by the probability that the door is open. So you kind of sum up over all the possible values for the door being open or closed. So plus the probability that we sense the door to be open, given that the door is closed, multiplied by the probability that the door is closed. So again, we can make these concrete using our sensor model. So the first term is exactly the numerator, so that's 0.6 multiplied by 0.5. And then the second term, we could get this term from the sensor model. So the probability that we sense the door to be open, given that the door is closed, is 0.2. And then multiplied by the prior probability that the door was closed, which was again 0.5. Okay, so the updated belief that the door is open is just the ratio of these, so 0.6 times 0.5 divided by 0.6 times 0.5 plus 0.2 times 0.5 is, what is it, 0.75. Which intuitively makes sense, right? So the robot is now more confident that the door is open, so it assigns a higher probability to the door being open, which makes sense given that it sensed the door to be open. So it's not absolutely certain, which again makes sense because the sensor is not perfect, but it's more confident than it was previously. So previously it just had a 50-50 chance that it assigned to the door being open. Now it's 0.75 confident. And then I guess we can also write the other possibility. So the probability that the door is closed is just 1 minus this. So the belief that the door is closed is 1 minus 0.75, which is 0.25. Okay. All right, any questions on these calculations? So I think it's maybe just to make the point about Bayes' rule again, it's interesting to see what role Bayes' rule is playing over here. So we applied Bayes' rule right there. Right, so what we want to calculate is the probability that the door is open given that we sense the door to be open. What we actually have is kind of the inverse, which is the probability that we sense the door to be open given that the door is open. So that comes from our sensor model. We also have this prior belief about whether or not the door is open. The denominator you can calculate just from those same conditional probabilities and the prior probabilities. And so Bayes' rule is kind of allowing us to do the inverse, to go from the sensor model to an updated belief about the state of the world. All right, so let's make it a bit more interesting. So far we haven't really accounted for any dynamics in the world, right? So the door is not changing its state just yet. We just looked at the very first time step. But yeah, let's make it a bit more interesting and think about dynamics as well. So let's say the robot has some action. So some control input that it can apply, which corresponds to just pushing the door. So there's only, let's say, one action that we're going to consider. So it can only push the door, or I guess it can do nothing. So again, we need some model about how the state of the world will change if the robot takes this action. And again, we're going to use probability distributions to represent this model on the dynamics of the system. So I'll just write it down, and then we'll kind of intuitively think about what it means. So the probability that at time step t, the door is open, given that at time step t minus 1, so the previous time step, the door is open, and the control input that the robot applied at the previous time step is equal to push the door, that's the only action we're considering right now, is equal to 1. So what this is saying is that if the door was already open at the previous time step and the robot pushes the door, then it's just going to remain open with probability 1. And so the probability that the door is closed, given that the door was open and the robot took this action of pushing the door, is just 1 minus that, which is 0. And then, yeah, I guess the other version, so the probability that the door becomes open at the next time step, given that at the previous time step the door was closed, and again the action that the robot took, the control input that it applied, is pushing the door. In this case, let's say that the probability is 0.8. So if the door was closed and the robot pushes it, it has an 80% kind of success probability of opening the door. And finally, the probability that the door is closed at the next time step, given that it was previously closed and the robot pushed the door. So this is just 1 minus 0.8, which is 0.2. All right. And again, we can think about how one might acquire such a probabilistic model. Again, you can think of doing a bunch of experiments. You take the robot, put it in front of many doors, and look at the probability that the door becomes open if it was already open, and the probability that the door becomes open if it was closed, and you empirically measure these probabilities, and then we call that our probabilistic dynamics model. All right. So at the next time step, so I'm going to keep this unerased. We'll need the numbers. So, all right. So at the next time step, so we've done one time step. So at time step 1, the robot sensed that the door was open. We updated our belief about whether or not the door was open, given that information. Now, suppose at time step 1, the robot pushes the door. And so the question is, how can it update its belief about whether or not the door is going to be open or closed once it's taken this action. All right, so let me see. I guess just to recap, where do the numbers go? Oh, right there. So before it does this, the robot assigns a probability of 0.75 to the door being open, 0.25 to the door being closed. So now it pushes the door. Now it needs to update its belief. And then I guess what's going to happen, just to preview a little bit, is that it's going to receive another sensor measurement. And that will help it refine its estimate of whether the door is open or not at the next time step. So I guess I'll say at t equal to 2, the robot receives another sensor measurement. And let's say again that at the next time step at t equals to 2, it senses that the door is open. So what we're going to do is something pretty analogous to the non-deterministic filter. So we're going to break up our updates into 2 steps. So the first step we're going to call the dynamics update. And the intuition behind this is we propagate our previous belief, which was 0.75, 0.25, through the dynamics of the system, given that we know that the robot has pushed the door at time step equal to 1. So that updated belief, we're going to denote with a bar. So belief bar is what happens when we update our belief, given just the knowledge of the dynamics, not taking into account yet the new sensor measurement that the robot receives at time step 2. So belief bar, that the state of the door at the second time step is open. I guess how should we calculate this? Any thoughts? So we know the action that the robot took, right? So it's pushing the door. Yeah, I guess how can we calculate its updated belief, knowing that it pushed the door? Go ahead.
You can use phase rule again, the belief that the second state is open is the same as the belief that the second state is open given that the previous state was open and that our action was the close, but also because of some of the law of probability.
Yeah. Yeah, so actually it's just the law of total probability here that we use. So this is the probability that the door is open at the second time step, given that we pushed the door. So this is the probability that the door is open, given that previously it was open, and that we took action which is pushing the door, multiplied by the previous probability that the door was open. So we're just applying the law of total probability, so plus the probability that the door is open, given that previously the door was closed. Again, the action was just pushing, multiplied by the probability that the door was closed. Right, so we're just enumerating the possibilities for the previous state. So it's just either open or closed. All right, so I guess the next question here is like, what are these probabilities? What should we take here? So the prior probability that the door was open versus closed. So these two terms over here, what are they going to be? Go ahead.
Substitute on a prior belief.
Yeah, so we already have a belief, right? So it was 0.75 and 0.25. So 0.75 for the door being open, 0.25 for the door being closed. So this is our prior belief before we kind of incorporate the knowledge that we pushed the door. Right, so we can just, I guess, calculate this. We already wrote down a couple of the terms. So these two terms are given by our probabilistic dynamics model, which we wrote over there. So P of x2 being open, given that the door was already open and the robot pushes it, so that's equal to 1 multiplied by 0.75. And then the second term, the probability that the door becomes open, given that it was previously closed, so it's 0.8 multiplied by 0.25. So if you multiply this out, so it's 0.95. All right, so the robot becomes even more confident that the door is open, which again makes sense because it pushed the door, and usually when you push a door, it becomes open. And it was already reasonably confident, so like 0.75 confident that the door was open at the first time step. All right, so I guess the final step here is to incorporate the new sensor measurement. So this is where Bayes' rule comes in. So step 2 is the measurement update. And we said that we're assuming at the second time step the robot receives a sensor measurement which is telling it that the door is open. So again, we'll represent this updated belief as BEL belief that the door is open. So really this is like shorthand for saying that the probability that the door is open, given that we received this sensor measurement at the second time step, which is that the door is open. So this is where Bayes' rule comes in. Again, we can kind of invert this conditional probability. So this is the probability that the door is sensed to be open, given that the door was open, multiplied by the prior belief, divided by the total probability of receiving this sensor measurement. Yes, question.
Shouldn't it be the belief that x2 is open, given that we're taking the action?
Yes, sorry. There's an action here as well. Yeah, thank you. So U1 equals push. So given two things, one that we push the door and that we sense the door to be open. Thanks. Okay. All right, so this first term we're going to again get from our sensor model, which was over there. So that's the probability that the door is sensed to be open, given that the door is in fact open, so that was 0.6. I guess the interesting term is this one. So the prior probability that the door is open. So what do you think that is going to be? Go ahead. 0.95, yeah. So that's basically our most up-to-date knowledge about whether or not the door is open. The most up-to-date knowledge takes into account the dynamics of the robot, well, I guess the door, and so that was 0.95. So we can, yeah, again, just, I'll write it here. Look at both the numerator and the denominator. So the numerator is, what did I say, 0.6. So that comes from our sensor model multiplied by 0.95. And the denominator again, we can use the law of total probability to expand this out. So that's the probability that we sense the door to be open, given that the door is open. Sorry, I'm going to run out of space here. Multiplied by, actually, I'll just write it over there. I think I can erase this. All right, so the denominator so that was the probability, the total probability that the door is open. So that's P of Z2 is open, given that the door is open, multiplied by this prior probability that the door is open, plus the other possibility. So the door is open given that, or door sense to be open given that the door is closed. Multiplied by this. So the first term is the same as the numerator, so you're always going to have this. So one of the terms in the denominator when you do this expansion is always going to be the same as the numerator. So that's 0.6 times 0.95. And then the second term we can get from our sensor model again. So the probability that the door is sensed to be open, given that the door was closed, was 0.2. Multiplied by our prior belief before we incorporated the sensor measurement that the door was closed, which was 0.95 minus, 1 minus 0.95, which was 0.05. So 0.95 was the belief that the door was open, so 0.05 is the belief that the door is closed. All right, so if you then just take this ratio, so the new belief, so at the second time step, that the door is open is, if you just take the ratio of these, it's about 0.983. So the robot is now very confident that the door is open. Again, this makes sense. So initially it was just kind of like 50-50. It sensed that the door is open, so that made it 0.75 confident that the door was open. And then there were kind of like two additional pieces of information that increased its confidence. So one, that it pushed the door, which made it believe even more that the door was going to be open, and then sensed that the door was open. And that made it about like 98.3% confident that the door is open. All right. So let's maybe just like think about the structure of what we did over here. So there were like these two steps, right, in the second time step. So one was the dynamics update, the second was the measurement update. And these are pretty analogous to the non-deterministic filter. So the first step, the dynamics update, is basically propagating our previous, sorry, question, yes?
Does it matter what order you do it in, like the dynamics or the second step?
So I guess how would you do? Oh, I see. So you would just take into account the sensor measurement and then like plug in the prior belief without the dynamics and then update that through the dynamics?
Yeah.
Yeah, that's a good question. Let me think about this. I think I would need to write it out. I don't know the answer off the top of my head. Yeah, I guess is there an intuitive way to figure it out? I think it matters, but I'm not absolutely sure. I'd have to write it out. The reason I think it matters is like just the kind of like semantics of it. So where if we incorporate the sensor measurement, that's telling us something about time step 2, right? So we're saying that our belief that the door is open or closed at time step 2 is something like given that we sense that the door was open or closed. To do the propagation, yeah, actually I think it doesn't quite make sense to do it the other way, right? So I guess how would you propagate that forwards in time? So we've already updated our belief at time step 2. And so we're not going to propagate it to time step 3 yet, right? So we still care about going from time step 1 to time step 2. So I think the only order that really makes sense is to take the previous belief, propagate that through the dynamics, and then update it with the sensor measurement. I think that's right. I guess does someone see whether or disagree with that? Okay, I think that's correct, but I don't know. Do you disagree with that or
it's kind of hard for me to
yeah, I think that's correct. Because yeah, I feel like it doesn't quite make sense to do it the other way because we're updating our belief at time step 2 and then we don't want to propagate that to time step 3. We want to propagate the previous belief to time step 2. So I think the other order doesn't make sense. But yeah, again, I'd have to write it out to be absolutely certain. It's a good question. Question?
In practice, it seems like this measurement update can be done multiplying because I assume that sensor measurements can come at a higher frequency than actions. That you can just do a measurement update sort of arbitrarily as many times as you want prior to the next update.
Yeah, so right now we were kind of assuming that the dynamics update and the sensor measurement updates happen concurrently in time, or like, yeah, simultaneously. And so the robot is taking actions at every time step. Yeah, I guess what you're saying is like maybe the robot takes actions at a lower frequency, so maybe it takes a while for the robot to like push the door, and in that time it receives multiple sensor measurements potentially. In that case, you could do a bunch of updates with just the sensor measurements, and then as soon as you get some information about the action that the robot took, you incorporate that as well. Yeah. Yep. Does that answer your question, or?
Yeah.
Okay. All right. So let me just write down. Yes, question.
So if I'm understanding this right, so does the robot take an action and that leads to this dynamics update, which is the belief?
Yes.
And senses and gets updates to the belief.
Yes. Yeah. So that's exactly actually. Let me just. I'll write down the steps. Kind of generically. Okay, so at each time step, so just to abstract this away and make it more general, so at each time step t, we're doing 2 steps. So the first one is the dynamics update. So we're getting this updated belief, which we're representing with the bar, belief bar. And actually this is for, so we calculate this for all possible values of xt. In our simple example, there were just 2 possibilities. The door was either open or closed. In general, the state of the world might have many possibilities. So yeah, the first step is summing over. Oops. So we're just applying the law of total probability. So we sum over the previous possible states of the world of the probability that the state at xt, the state at time step t is xt, given that at the previous time step it was xt minus 1, and you took action, so you applied a control input ut minus 1 multiplied by the prior belief, so the belief at time step xt minus 1. And then the second step is to incorporate the sensor measurement. And this is done with Bayes rule. So this is the probability of xt given zt multiplied by, the other way around. Probability of the new sensor measurement given a state multiplied by our prior belief having taken into account the dynamics. Bar divided by P of ZT. So this is again called the dynamics update. And this step, the second step, is called the measurement update. And I guess, one point I want to just emphasize again is that this is similar to what we were doing with the non-deterministic filter. Right, with the non-deterministic filter, our representation of uncertainty was just a set. So a set of possibilities that the robot could be in. Here it's more refined, it's a probability distribution. We're taking our previous probability distribution, so our previous belief about whether the state was at the previous time step, xt minus 1, and propagating that through the dynamics of the system. And then we're incorporating our sensor measurement, and that's where Bayes rule comes in. So this is exactly Bayes rule. All right, so this, I guess, kind of general algorithm, so this is called the Bayes filter. And okay, so if we have a discrete set of possibilities for the state of the world, so if x, the state of the world can take on finitely many values, discretely many values, so then this kind of makes sense, like we're summing over those possibilities. In the continuous case, so in the case where, let's say, you have a drone, right? So in that case, the states are not discrete, rather they're continuous. In that case, the only difference here is that we replace anything that has a summation with an integral, but the general structure is kind of exactly the same. So that's, I guess, one comment. The other comment is, so I haven't really given you a formal justification for why this makes sense. I mean, I think the justification is that it's pretty similar to the non-deterministic filter. We do a dynamics update, then we do a measurement update. But yeah, if you want to see more like details and justification, this is in chapter 2.4.3 of the probabilistic robotics books. It goes through a more kind of careful derivation of the Bayes filter. The other comment is that the Bayes filter is like pretty computationally challenging to implement. If you have continuous states, so continuous valued states. So for our simple example, the state of the world could take on just two possibilities, so we could basically do everything by hand. In a slightly more general setting, maybe the state of the world can take on finitely many values, and then you have to calculate the summations. If the number of terms is relatively small, then it's fine. But I think it gets really challenging when the summations get replaced by integrals, so when you have continuous valued states, and then integrals become pretty hard to calculate analytically. Question?
So for this system, do we have an initial belief?
Yes. Yeah, I guess that's a good point. So I didn't write it here explicitly. Implicit here is that we have some initial belief, which we were saying was just like 0.5 for the door example. But yeah, that's a good point. This assumes that you started off with some initial belief that you then propagate to the first time step, and so on. Okay. Yeah, I guess the last comment I want to make is that, so there's about this computationally challenging part. So there are certain settings where one can actually implement these two steps, so the steps in the base filter analytically and like very computationally efficiently, even in the case where you have continuous valued states or sensor measurements. So specifically, if you have linear dynamics and a linear measurement model, and I'll say a bit more about exactly what that means, and if you assume Gaussian uncertainty, it turns out that one can computationally efficiently implement the base filter and exactly, so there's no approximation there. And this leads to something called Kalman filtering, which we'll discuss in the next lecture. In general, this is not possible to implement exactly in a computationally efficient manner. And so we have to make some approximations. And yeah, I guess one of the really popular techniques for approximately implementing the base filter is called particle filtering. Yeah, which is very widely used in practice, which we'll also discuss in the next lecture. All right, I guess any final questions? Cool, so I'll see you after a break then.